Hello friends, good morning to all of you. It was the year 1820 in which so many significant events took place in the field of the science. One of them was the discovery of the Antarctica and another one was the magnetic fields due to the current discovered by the Oersted. And inspired by the Oersted, two French scientists, that is one of them is the Biot and another one is the Savart, have derived an expressions for magnetic field at a point due to a small current elements, and that expressions is dB equal to mu naught by 4 pi I dl sin theta by r square. They have done the research in this field. They have find out the value of the magnetic field due to a small current elements. So today our topic of discussion is the Biot-Savart law in this video lectures. Before understanding this Biot-Savart law, we have to understand about what is current elements. In order to understand the current elements, let's see here. Suppose this is a wire, this is our wire, and this wire okay. What I was discussing was that the current elements. So this is wire. This wire can be divided into a very small segment, very small segment, and that small segment carrying current is known as the current elements. But now the question arises, how much small that segment can be, because smallness or biggerness, bigger, this is a relative terms. One line can be considered as a small and another line, same line can be considered as bigger, because it is a relative terms. Suppose this is a line, this line is smaller than this line, but this line is greater than this line. So it is a relative terms. So what I have told you is that I am going to divide this line segment into very small part, very small part, and a small part of the line segment carrying current is known as the current element. But this length can be considered as small when it is compared with something. Without comparing it, we can't say this length is small in size. So this length, a small current elements, it is compared with the length of the r. This is the distance between the point P, this is our observation point, and this is our small current elements. Comparing, we compare this small current element with this r. If the value of the dl, is very less than r, then we say that dl is a current element. dl is a current element. I am going to explain you with the help of the example, then it will become clear. And dl is a current element. It is a vector quantity, so we have to introduce this arrow here, and the directions of the dl is in the directions of the current. So we can say that the current element is a small segment of the wire carrying current, and it is represented by the dl vector, and its direction is along the current carrying wire. Okay. So let's see how to derive, how Biot and Savart has derived these expressions. dB equal to mu naught by 4 pi I dl sin theta by r square. This is the Biot-Savart law, how they have derived it. So let's see it. So So suppose this is a wire, carrying current, I, and this length, this, and this one is the small current elements, and the directions of this current element is in this way, and this is our point of observations. P is the point of observations where we want to find out the magnetic fields. What is the value of the magnetic field here? So Biot and Savart has done so many experiments, and on the basis of the experiment they found that the magnetic field at point P is directly proportional to the current. That here I have represented this magnetic field with dB. Why I have represented this magnetic field with dB? Because this magnetic field is produced due to a small current elements, and the magnetic field which is produced due to a small current elements can be will be always smaller in size, will be smaller in magnitude. Okay, so that's why I have represented this magnetic field with the help of the means in the differential forms, and differential form it is represented as dB. So Biot and Savart has done the experiment, and on the basis of the experiment they found that this magnetic field at point P is directly proportional to the current carrying conductors. How much amount of the current is moving in this conductor? On the value of that current, this magnetic field depends. If the amount of the current in the conductor is more, then the value of the magnetic field is also more. If the amount of the current in the conductor is less, then the magnetic field is also less. It is having the directly proportional relations, directly proportional to the I. Second, they have found out that dB is directly proportional to dl. dB is directly proportional to dl. What does it means? It means that the magnitude of the magnetic field is directly proportional to the length of the current element. Here dl is the current elements and dl represents the length of the current elements. If the length of the current elements is more, then the value of the magnetic field will be more. If the length of the current element is less, then the value of the magnetic field will be less. And again, dB is directly proportional to sine theta. It is directly proportional to sine theta also. Sine theta. And theta is the angle between this dl and r. This is our dl portion and this is our r portions, and we have to measure the angle from dl to r. From dl to r, we turn our hand from dl to r, and in that case we will measure this angle and take the sine theta of that angle, and we find that dV is directly proportional to the sine theta. So I dl sine theta, and last one they found out that dV is inversely proportional to the square of the distance between the point P and the dl. Here the distance between the point P and the dl is r, and they found out that this the magnitude of the dV is inversely proportional to the square of the distance between them. It means if the distance is increasing, the magnitude of the magnetic field will decrease. If the distance is decreasing, the magnitude of the magnetic field will increase. Means it is having the inverse relation. So combining all these four equations, when we are going to combine all these four equations, what we are having, we get that dB is directly proportional to I dl sine theta by r square. This is what we get. dB equal to I dl sine theta by r squares. Now in order to remove this proportionality sign, we have to introduce some constant. So let k be the constant. So when we are going to introduce constant, dB, it becomes k I dl sine theta by r square. This is Biot-Savart law. which is used to find out the magnetic field at point P, which is at a distance of r from the current element dl. Now the question arises, what is the value of this proportionality constant K? This value of the proportionality constant K depends upon the types of the unit we have selected. If we are going to select SI units, then in that case the value of the K will be different, and if we are going to select CGS system of the unit, in that case the value of the K will be different. If system is changed, then the value of the K is also changed. So the K depends upon the types of the system we have chosen, and it also depends upon the medium which is between the P and the DL. Suppose this is P and this is our this is our DL current elements, and there is a medium, some medium is between this observation point. It can be either glass. Suppose I have put a glass between the point P and the current elements, and in next case I put the water between this point P and the DL. So in both the cases the value of the constant will change, because K depend upon what type of the medium is between the point P and the DL. So if we are taking this medium as a free space or vacuum, if there is a vacuum between the DL and the P, and if we are going to select the SI system of unit, then in that case the value of the K is mu naught by 4 pi. So in that case the value of the K is mu naught by 4 pi, that is we are having the expressions dB equal to mu naught by 4 pi I dl sin theta by r square, ideal sin theta by r square. This is our the final expressions for the Biot-Savart law in order to find out the magnetic field at P. Here mu naught by 4 pi is a constant, and its value is mu naught by 4 pi is 10 to power minus 7 Tesla meter per ampere. Tesla meter per ampere, this is its value, mu naught by 4 pi value. Mu naught is known as the permeability of the free space. It is known as the permeability of the free space. Now the question arises, what is the meaning of the permeability? What is the meaning of the permeability? Permeability means to what extent the material or the medium get magnetized when it is placed around a wire carrying current. To what extent it is getting magnetized? Suppose here, suppose I have put some medium here, and when I am going to put this medium, suppose this is A type of the medium, and when I put this A medium besides this wire, I find that it is getting highly magnetized. It is getting highly magnetized. It means here the permeability of this medium is very high. Permeability is high. But if another medium, suppose B, I am keeping here another medium B, and if it is getting slightly magnetized, means it is not getting more magnetized, it means permeability is less. So permeability tells us to what extent the medium is magnetized when it is kept around the, or when it is kept near the magnetic field. So same, so this is what I have explained it, also known as the magnetic permeability. Magnetic permeability. This is known as the permeability, is also known as the magnetic permeability. It indicates to what extent a material or the medium can be magnetized when placed inside an externally applied magnetizing field. if we put any medium or material in an external magnetic field, then in that case if we it will tell us to what extent it is getting magnetized, and that thing represents the permeability, means permeability represents this one. So mu naught, permeability of the free space is represented by the mu naught, and the permeability of the medium is represented by mu, and relative permeability of the medium is represented by mu r, and both are having the relations that mu r equal to mu by mu naught. This is the relations between the relative permeability, and this is the permeability of the medium, and this is the permeability of the free space. And mu naught, as I have told you, it is the permeability of the free space having the value 4 pi into 10 to power minus 7 Tesla meter per ampere. This is the value of the permeability of free space. Okay. So we have discussed Biot-Savart law. Its expression we have discussed it, that is dB equal to mu naught by 4 pi ideal sine theta by r squares. How it was derived, we have discussed it, that it has been derived experimentally. They have done so many experiments, and on the basis of the experiment they have derived this expression, and the value of the constant depends upon the types of the medium selected between the observation point and the DL, and the types of the unit chosen. Okay. So one thing I have left is that the current element. I have told you that the length can be either long, it can be considered as larger in size or a smaller in size, because it is a relative terms. Suppose here we are having the wire. Suppose this is a wire, and I am interested to find out the magnetic field at point P, which is at a distance of 100 centimeter, then I am taking a length of 1 centimeter on the wire AB. This 1 centimeter is very less compared to the 100 centimeter. 1 centimeter is very less compared to the 100 centimeter. So 1 centimeter can be considered as a current element. This the length of the current element is 1 centimeter, because it is compared with 100 centimeters. But if this is our 1 centimeter length on the wire, 1 centimeter, and I am interested to find out the magnetic fields at some distance. Suppose I am interested to find out at 0.5 centimeter distance from this wire. Then in that case this 1 centimeter cannot be considered as a current element, because 1 centimeter is not very less than 0.5. Actually it is greater than 0.5 distance. This is the distance of the point P. How much it is? 0.5 centimeter. So in this case 1 centimeter can't be considered as a current element, whereas in this case we can consider 1 centimeter as a current element, because here 1 centimeter is very less compared to 100 centimeter, but here 1 centimeter is not so less than 0.5 centimeter, it is bigger than 0.5 centimeter. So it is a relative term. So we have to compare it with r. This is the distance r between the observation point and the DL. So always compare the length of the wire with the r, and if it comes out to be very small, then that length can be considered as a current element, and its direction will be the directions of the current. Okay. So we have understood the current element also, and we have also understood the magnetic derived an expression for the Biot-Savart law. So let's find out what is the directions of the magnetic field at point P. Here P, a magnetic field is produced. So what is its direction? So how to find out the directions of the magnetic field at P? So in order to find out the directions of the magnetic field, directions of the magnetic field at point P, it is given by the right hand screw rule. It is given by It is given by right hand screw rule. What does this right hand screw rule tells us? That this is our current carrying wire, and I am interested to find out the magnetic field at point P, and this is DL having the current in this directions, and this is R. Okay, this is the distance. R is the distance of the point P from this current element, and its direction is in this direction. Its direction is always away from this current elements towards the P. So this is our angle. Put a screw, means right hand screw, put it here means especially put it here, right hand screw, and rotate it from in the directions of the theta. In the directions of theta means rotate it from DL to R. Put a right hand screw here and rotate it from DL to R. The directions of the DL is in the upward directions, and this directions of the R is in this directions. So when we are going to rotate it, see the advancement of the right hand screw. If the advancement is inside the board, it means the directions of the magnetic field will be inside. But if the advancement of the screw is outside, if it is coming out, then the directions of the magnetic field will be out of the board. So if you are going to put here a screw and rotate it from DL to R directions, means in this directions. So what we are going to observe is that it is going inside the board. So the directions of the magnetic field will be here inside the board, and it is represented by this cross sign. Okay, if it is inside and it is perpendicular, it will be always perpendicular to the DL and R. And if by rotating the screw here, it comes out, the advancement of the screw comes out, it means the directions of the magnetic field will be out of the board, and it will be, in that case, it is represented by dot. Magnetic field is into the board. Into the board here, magnetic field is out of board. It is out of board. So these are two representation which is used to denote the directions of the magnetic field. If the directions of the magnetic field is inside the board or into the page, then it is denoted by the cross sign, and if it is out of the page or out of the board, then it is denoted by this dot signs. Generally this magnetic field is always perpendicular to the DL and R. DL and R, it lies in the same plane. Suppose DL and R lies in the XY axis, means suppose this is X axis and this is Y axis, and in this X axis lies the R and in Y axis lies the DL. Then the directions of the magnetic field will always lie in the Z axis. It will lie in the Z axis, either positive Z axis or in the negative Z axis. It depends upon how the screw is rotated. How means in which directions the current is flowing in DL. It depends upon this one. Okay, so we here find out that the directions of the magnetic field is always perpendicular to the DL and R, and it is find out with the help of the right hand screw rule. Or without the help of the, without using the right hand screw rule, you can also make use of this finger. Just turn this finger. Here the directions of the DL is in this directions and the R is in this directions. Turn this forefinger from DL to R, and see the in which directions this thumb point. And in this case we find out that if we are going to rotate this our forefinger from DL to R, this thumb is pointing inside the board, into the board. So here in this case the directions of the magnetic field will be into the board. Okay. So next topic, So let us study some of the special cases. We have seen the Biot-Savart formula. We have seen the Biot-Savart formula, that is dB equal to mu naught by 4 pi I dl sin theta by r square. This is our Biot-Savart law or Biot-Savart formula. So if the value of the theta is 0 degree, then in that case what will be the value of the sin theta? Sin 0 degree will be the 0, then this whole case will comes out to be 0. So if the value of the theta is 0, then the value of the magnetic field will be 0. What does it means theta is 0 degree? It means that suppose this is our wire and here I am going to find out the magnetic field at point P, and this is our current element. A, B is our current element represented by dl. Then here this is the length of the this AB is the dl. This is the length of the dl. AB we have considered it. We are going to find out the magnetic field at the point P, and this is our theta. This is our theta. This is the direction of R and this one. So here this is the axis of the dl. Means draw a straight line containing the dl. So this blue line indicates the axis of the dl. If our point P lies on this axis of the dl, then in that case the angle between the value of the theta will comes out to be 0, because it is lying on this line. Here it is the point P and this is the dl. It means both the lines are parallel. dl and r both are parallel to each other, means both are same lines. It means here the value of the theta will comes out to be 0. So in that case, in this case, the value of the dB will comes out to be 0. It means if the point P lies on the axis of the current element, then the value of the magnetic field will be 0. So that is what I have written it. The magnetic field is 0 at point on the axis of the current element. On the axis of the current element, and the axis of the current element means a straight line containing the dl. A straight line containing the dl means draw a straight line having the portions of the dl that will be that is known as the axis of the current element. But if the value of the theta is 90 degree, and we know that sin 90 degree equal to 1, and it is a maximum, the maximum value of the sin theta is 1, it means the value of the magnetic field will be the maximum. So if theta is 90 degree, the magnetic field will comes out to be maximum. Means here it is we are having the point P and here dl. If the angle between this dl and r is 90 degree, then in that case the magnetic field will be maximum due to this current element. Okay, got it? Okay. So let's see the SI unit of the magnetic fields. We have discussed the Biot-Savart law. SI unit of the magnetic field is the Tesla. Tesla is the SI unit of the magnetic field. So SI unit of the magnetic field. SI unit of the magnetic field is the Tesla, and we are going to define Tesla in terms of in terms of Biot-Savart law. So let's see how we are going to define Tesla in terms of the Biot-Savart law. We know this is our Biot-Savart law, dB equal to mu naught by 4 pi I dl sine theta by r square, ideal sine theta by r square. So what I am going to do is that take the value of the current as 1 ampere, take the value of the current as 1 ampere, and the length of the current element should be 1 meter. I have taken it in the SI system. The length of the r is 1 meter and the sine theta to be 1. If all this value, this is 1, this is also 1 meter, this value is 1 and this value is also 1, then in that case dB equal to mu naught by 4 pi it is coming, and its value is 10 to power minus 7 Tesla meter per ampere. This is the value. So this value comes out to be dB equal to mu naught by 4 pi 10 to power minus 7 Tesla. And if we are going to take this 10 to power minus 7 to this side, so what will become? This is 10 to power minus 7, and when it comes to this side it will become 10 to power 7. How it becomes? Let's see. dB equal to 10 to power minus 7 Tesla. dB, I am bringing this 10 to power minus 7 to this side, 10 to power minus 7 equal to 1 Tesla. So dB, this 10 to power minus 7, when it goes up it will become 10 to power 7 dB equal to 1 Tesla. So how much we are getting it? 1 Tesla equal to 10 to power 7 dB. So in this we are getting a relationship between Tesla and the magnetic field due to Biot-Savart law. Means with the help of the Biot-Savart law we have derived an with that expressions we have find out the magnetic field. So we are going to define 1 Tesla. 1 Tesla is 10 to power 7 times. 1 Tesla is 10 to power 7 times the magnetic field produced by a current carrying wire having 1 meter length, carrying a current of 1 ampere and at a distance of 1 meter and the angle is 90 degree. Then in that case the value of the magnetic field is known as the 1 Tesla. How we have described it? 1 Tesla is 10 to power 7 times the magnetic field produced by a conducting wire of length 1 meter. Length should be the 1 meter of the wire, and that wire should be carrying a current of 1 ampere, and the point of observation should be 1 meter from it and perpendicular to it. Then in that case 1 Tesla will comes out to be 10 to power 7 dB. Let me explain it again. Suppose this is a current carrying wire and this is A and B. This is our DL in this directions, and this is our point of observations. It is at a distance of 1 meter, and here the angle is 90 degree. Here the angle is 90 degree, and it is carrying a current of I equal to 1 ampere. Then due to this wire a small magnetic field is produced here. A small magnetic field is produced here, and that is represented by the dB. Then 1 Tesla equal to 10 to power 7 of dB. 10 to power 7 of dB. Okay, are you getting it? Means we have to take everything as a unit value. At a distance of 1 meter, current carrying is 1 ampere, and the value of the angle is 90 degree. Then in that case we are getting this relations that 1 Tesla equal to 10 to power 7 dB, and this dB can be find out with the help of the Biot-Savart law. Okay. Now let's see the Biot-Savart law in vector form. In vector form, how we can find out? It was experimentally find out that the directions of the magnetic field is always perpendicular to the DL and R. Experimentally they have find out it is always perpendicular to the DL and R. And we know about the cross product, that is A cross B equal to AB sin theta n cap. And this n cap represents the directions of a vector which is perpendicular to both A vector and B vectors. So dB equal to mu naught by 4 pi I dl sin theta by r square. What I am going to do is that mu naught by 4 pi I dl sin theta, I am going to multiply here r and going to divide it with the same r, and here it is r square. I have multiplied here and I have also divided here. It means it will cancel out. This equation is equal to this given equations. Okay. Now mu naught by 4 pi I dl r sin theta by this thing I am going to multiply it. This is r cube. Now dl r sin theta, what it comes out to be? We know the cross product A cross B is AB sin theta n cap. AB sin theta n cap, this is the value of the cross product. Here it means the directions of this this vector is perpendicular to A and B. It is always perpendicular to A and B. And here also experimentally it has been find out that the directions of this dV is always perpendicular to the dl and r. It means we can arrange this dl sin theta and r in this term, dl r and sin theta. And experimentally it has been find out that its directions can be find out by rotating the right hand screw from dl to r. That's why I have written dl before then r. Are you getting it? So if we are going to combine this, we are getting as mu naught by 4 pi I, this dl r sin theta will become dl cross r vector by r cube. This is the magnetic field. This is the expressions for the magnetic field given by the Biot-Savart law in vector forms. That is dB equal to mu naught by 4 pi I dl cross r by r cube. This is in the vector forms. Okay. And this vector forms, what does it tells us that this, in order to find out the magnetic field, we have to do the calculation in 3D. We have to do the calculation in 3D because this cross product always involves the 3D directions, means 3D axis, means all the 3 axes is involved. Because suppose this A is in this directions, x axis, and B is in this y directions, then when we are going to do the cross product, it will gives a vector whose direction will be in the z axis. Means cross product involves all the 3 axis calculations. Okay. So Biot-Savart law can only be expressed in differential form. It can be expressed only in differential forms. That's why we are having the dB equal to mu naught by 4 pi I dl sin theta r square in differential forms, and it requires working in 3 dimensions because of the cross product. Since there is a cross product, it requires the since there is a cross product, it requires the calculation in 3D. 3D axis we have to 3 dimensions we have to do the calculations. Okay, this thing we have got it. This thing we have explained it. Again, after that, just for extra informations, it is not in your syllabus. Just know it. In order to what are the applications of the Biot-Savart law? Its application is to calculate the magnetic responses even at the atomic and the molecular level. Even at the atomic and the molecular level, you can calculate the magnetic responses, and it is also used in aerodynamic theory to find out the velocity. It is just for knowledge. This is in your syllabus, Biot-Savart law versus Coulomb's law. Biot-Savart law versus Coulomb's law. In case of the Coulomb's law, we know that this is given by, according to Coulomb's law, the electric field produced by charge element at a distance r is given by 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught dq by r square. This is the formula of the electric field. And in case of the electric field, charge is the source. Charge is the source. And in case of the Biot-Savart law, we have seen this formula mu naught by 4 pi ideal sine theta by r squares. So we want to compare it, we want to study it, means we want to find out what is the similarity between Biot-Savart law and what is the similarity between this Coulomb's law, which has been used to find out the formula for the electric field. What is similarity between both these two equations? So if we are going to see it, we see here is that this d is inversely proportional to r square. D is inversely proportional to r square, and here also dB is inversely proportional to r squares. In both the cases, electric field and the magnetic field are having the inverse relations with the distance. And how they are increasing or decreasing? With the square of the distance. With the square of the distance, they are either increasing or decreasing. It means distance is having the very effect in case of the electric field also, and in case of the magnetic field also. So this is the similarity. Okay. And what is the difference? What is the difference between these two things? The difference is that here the source of electric field is the dq. Here the source of the electric field is the charge. But in case of the Biot-Savart law, the source of the electric field is current, means IDL. This DL, actually the current element is the source of the magnetic field. Current element means carrying DL vector in this form, DL vector. It means it is a current element. Here it is the source. So these are the some of the similarities I have written here. Both the fields depends inversely on the square of the distance from the source point to the observation point. A square of the distance pe it depends upon the square of the distance. If it increases, then the value of the field will decrease, and if it is decreasing, then the value of the field will increase. Both are long range fields. Both are long range fields. In case of the nuclear force, it is a very short range force, means it exists inside the nucleus only. But in case of the magnetic field and the electric field, it exists to a very long distance. That's why it is both are long range fields, and the principle of the superposition is applicable to both the fields. What is the meaning of the principle of superpositions? In first chapter you must have studied it. So let's get a quick recap. Means principle of superpositions. Suppose we are having this here, we are having the Q1 point charges, and here we are having the Q2 point charges, and this is the point P, and we are interested to find out the electric field at point P. So here at electric field there at point P, there will be the electric field due to this due to this charge Q1. By applying the formula 1 by 4 pi epsilon naught Q1 by this distance square. This electric field at point P due to the Q1 remains unaffected by the presence of the Q2. Q2 is not going to disturb, Q2 is not going to change the value of the magnetic field at P due to Q1. Same in case of the Q2. Here at the point P, there will be the electric field also due to Q2, and its electric field is unaffected due to the presence of the Q1. None of the electric field, means none of the charge is going to change the value of the electric fields of other. Means they are just involved in themselves only. They are not going to disturb the other. This is known as the principle of superpositions. Means here suppose this charge is producing some electric field here as E1. So the value of the E1 will be always E1 due to this charge. and suppose this charge is producing the value of the electric field as E2, and here at point P it will be always E2 due to Q2. It is not getting disturbed due to Q1 or due to the presence of the other charges. This is known as the principle of superpositions. Means in both the cases, magnetic field and the electric field, in both the cases principle of superposition is applicable. If we are going to find out the either electric field or magnetic field at any point, then just find out the electric field or the magnetic field due to its source individually. Just find out individually, and finally just add it. If it is a scalar quantity, add it since it is a vector quantity, so add it according to the vectors. Other source does not disturb, means does not disturb the magnetic field produced due to the other sources. Okay, each sources contribute individually at that point of the observations. So these are some of the similarities. So let's see what are the difference, points of differences. What are the points of the differences between these two fields, electric field and the magnetic field? Magnetic field is produced by a vector source of the current elements. We have seen it. Ideal means DL is the current elements having the directions of the current. It is always produced by the current elements, but the electrostatic field is produced by the scalar source, that is the charge. Charge is a scalar quantity and charge is the source of the electric field. But in case of the magnetic field, a current element DL, ideal, it is the source. It is the source of the magnetic fields. The direction of the electrostatic field is always along the displacement vector. Always along the displacement vector. What does it means is that suppose this is Q1 and this is our point of observations. Here we are going to find out the electric field. Then its direction will be join this line Q1 and P. This is displacement vector. This is known as the displacement vector. So the directions of the magnetic field will be always along this line. So that is what I have written here, is that the directions of the electrostatic field is always along the displacement vector joining the source. It is always along this displacement vector. But in case of the magnetic field, we have seen in case of the Biot-Savart, if it is our point P and if this is our current element AB, its direction is in this, and this is our angle theta, this is R. Then at point P, in order to find out the directions of the magnetic field, we have to put a screw here and rotate it from DL to R. Rotate it from DL to R. And if we are going to rotate it, we find that the screw advances inward. It means the directions of the magnetic field is inward. So the directions of the magnetic field will be always perpendicular to the DL and R. But in this case, it is always along the displacement vector, that is the line joining the Q1 and the point of observations. On this, in this line will be always the directions of the magnetic field. Either it will be towards the P or it will be away from the P. It depends upon the nature of the charge. Direction of the magnetic field is perpendicular to the plane containing the displacement vector. This R is known as the displacement vector, DL to P, perpendicular to the plane containing the displacement vector, and this is our current element. It is always perpendicular, means either it will be outward or either it will be into the board. It depends upon what is the directions of the current here. Okay, so these are some of the points of difference. So finally, our lecture on the Biot-Savart law has been completed. So at last, I am stopping this lecture by this शायरी. That is what I have written here. बस यही सोचकर ज़्यादा सिकवा नहीं किया मैंने कि हर कोई अपनी जगह सही होता है. So this was our lecture. In next classes we will meet again, and in that classes we will discuss about the numerical based on the Biot-Savart law. So till that, have a good day. Bye. Permeability.